I will deal with that like after the class. Okay, so yeah, this is a data set that's like from that institute. So we try to create a model for this data set, and you can see that, okay, first like we use the zip regression. So we have psi, okay, which is like has a beta prior, okay, flat beta prior, and alpha, okay, is a very simple normal distribution, okay, with a non-committal Gaussian prior, and the beta, okay, by the way, remember we have two features, right? The where is it? Here, how many children we have in a group, and you know, whether or not we have a camper, okay? So I mean, obviously, because we have two features, we have two beta. So the shape is 2, and it's a normal distribution with a mean 0 and a standard deviation 10. So it's a non-committal Gaussian prior. And for the theta, okay, this theta is going to be this one. Where is it? This one. E to the power of alpha plus x beta. So you can see that, okay, theta is the pm.math exp inside the parentheses. It's going to be alpha plus beta 0 times fish data child plus beta 1 times fish data camper. This here, I mean, just want you to be aware that this fish data child by itself is also a count data. Obviously, number of number of children is also a count data. So, but that's fine. That's fine. You can still use it just like a regular, you know, numerical variable. Okay, but this camper is an interesting one. Okay, the camper actually is Boolean. Okay, whether or not indicating whether or not, I mean, this group has a camper. Okay, so 0 means no camper or false. 1 means this group has a camper, okay, or true. Okay, and because we can sort of explain this Boolean variable into 0 and 1, so we pretty much still treat it as a numerical data type and multiply this one by beta 1. Okay, this is fine, by the way. Okay, so then, okay, once we get this theta, okay, which is exponential of this thing, and then we put it in the zip, okay, distribution. We put the psi theta and the observed data, okay, which is you know, the count. Okay, this count is the number of fish they caught, okay, for each group, and then we generate 1,000 sample. That's it. Okay, and then, okay, we use the following code to generate the feature, generate the figure. Okay, so I think I will not go into a detail here. So you can see that in this plot, okay, the blue one the x value, coordinate x-axis indicate number of children. Okay, the y-axis indicate the fish caught. Okay, and obviously, like because the number of children is a count data type, so it only has a 0, 1, 2, 3, 4, up to 4. I mean, I think like for a family to have 4 children is already a lot. Okay, so the data set only has the maximum number of children that in the data set is 4, by the way. And also, I mean, the way, I mean, we have camper or not is represented by different group. Okay, the blue group indicated without camper. The orange group indicating like with camper. So you can see that, okay, with camper, okay, the family with camper tend to catch more fish, right? You can tell, okay, and also like this margin sort of diminish, okay, when you have more and more children, right? Okay, so here, I mean, the difference is more significant than, I mean, the difference between, I mean, when a family has 4 children, I mean, there's almost not much difference, okay? And also, like, when family has more children, it tend to catch lower fish, right? This is also something you can observe, which is very consistent, right? So, okay, for each additional child, the expected count of fish caught decreases by about 0.4. This can be actually, estimated, okay, easily. And being in a camper increases the expected count of the fish caught by about 2. But this value actually decreases as the more and more, as the family has more and more children, okay? And so we arrive at this value by taking the exponential of beta 1 and beta 2 coefficients respectively. So this one, okay, is basically like because how should I say? Here, because this is like or put it this way. Oh, I need to be careful. Okay, this one should be e to a power of alpha plus beta 0 x 0 plus beta 1 x1, right? That's theta is equal to this one, right? Right? So I mean, the first one, the first x0 indicate like the number of children in the family, right? Every time you have one more child, okay, you get one more beta 0, right? You get one more beta 0, and then one more beta 0 pretty much is one more beta 0 is like e to a beta 0 times the original one, right? Because the addition in the power, okay, will be translated into like something like this, right? Okay, so e to the power of beta 0, okay, indicate like when you have one more child, how many additional fish you catch. So that's why he said, like, okay, shoot. Okay, for each additional child, the expected count of fish caught decreased by 0.4. Okay, so, and also, whether or not you have a camper, okay, it's like, going to be affected by this beta 1 factor, right? This additional beta 1 factor in the power is going to be e to the power of beta 1, right? So e to the power of beta 1 is roughly 2. Okay, so that's being in a camper increases the expected count of fish caught by 2. So here is like how this is, analyzed. Okay, by the way. Okay, so we arrive at these values by taking the exponential of the beta 1 and beta 2 coefficients. Okay. So we just saw how to fix excesses of zeros without directly modeling the factor that generates them. Okay, so a similar approach suggested by Krusk. Okay, the Krusk is the guy who wrote, I mean, the other book, I mean, the very thick one. Okay, doing Bayesian data analysis. I mean, that's really actually a very good book. I mean, I used that for this class for several years. But the reason I stopped using that book is because that book used R. Okay, I mean, but in our department, we are not, the students are not into R that much. So I decided to switch to Python, to the one that's, I mean, based on Python. But to be honest, that book is a very nice one. Okay, remember like the MCMC slides I gave you. That chapter actually came from that book. Okay, it's a very the book has a very nice explanation for many different concepts. So if you are into, if you after this class, if you want to study a little more on Bayesian data analysis, I mean, but you are not into math part, you just want to know more about Bayesian data analysis, then the Krusk book is perhaps the best one that I can recommend. Okay, but anyway, okay, so Krusk actually also, you know, suggests like another approach, okay, which can be used to perform more robust version of logistic regression. Okay, so in logistic regression, we model the data as a binomial. Okay, so that is zeros and ones. Okay, so it may happen that we find a data set with unusual zeros and ones. Okay, so take as an example the Irish data set that we already saw, but with some added intruders. Okay, so this one, okay, yeah, we just obtain. I mean, we use the two different. We read the two different species, Setosa and versicolor. But okay, then and we use like a sepal length as our feature. But here, okay, we intentionally add like some additional. Let me see, y0. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. We add 6 additional data to, I believe it's like the Setosa. Okay, we add this 6 additional data, okay, with its corresponding features, okay, the sepal length, okay, into this data set. And this sepal length, okay, is unusually long compared with like a regular sepal length in Setosa, if I remember correctly. Okay, and then okay, obviously, I mean you center the data set and you can plot the data set and here. Okay, you can see. Oh, I'm sorry. I think the ones that get added are here. The 6 points are here actually. Okay, and those represent the top one. It should be, which way is which? I forgot. I mean, so they have like a much shorter sepal length. I remember the opposite. Okay, sorry. So these 6 additional data, I mean, unfortunately have like the shorter sepal length. Okay, compared with the other, you know, sepal length. Okay, of the same kind. Okay, so if that's the case, okay, you have some outliers. Okay, how do you deal with them? Okay, the way to do that is, you know, remember like that the zip approach that we use. Here we could do something similar. Okay, we have, you know, some. Oh, that's a versicolor. okay, with unusually short sample length. So we have the 6 additional vesicular with unusually short sample length. So we can fix this with a mixture model. Okay, this mixture model, the concept is just like a zip. Okay, so we are going to say that the output variable comes with the pi probability of random guessing, or with the 1 minus pi probability from logistic regression model. Okay, so mathematically, we have p equal to 0.5 to the pi plus, this is random guess. Okay, when you are, we have a probability pi to do the random guess. Because random guess, the probability is 0.5, right? So you just put the 0.5 directly here. And for 1 minus pi, we are going to do the logistic regression. This part is just like regular logistic regression. But this part is like, we intentionally to increase that amount of random guess. Okay, that random guess help us to accommodate those like special outlier cases. Okay, so then, okay, when pi is 1, we get p equal to 0.5. So that's a random, exactly, complete random guess. When for pi is 0, we recover the expression of logistic regression. So this model, okay, depending on the value of pi, you are able to accommodate different situations very well. Okay? So then, okay, obviously, as for what is the value of pi, it can be determined by the data. Okay, and obviously we are going to put a non-committal value to it. Okay, so okay, implementing this model is straightforward. Okay, so you have alpha, okay, beta, they are non-committal Gaussian, and mu is the alpha plus xc times beta. Okay, that's the sample length, right? Times beta, and the theta is going to be, you know, the sigmoid mu. Okay, this part is exactly the same as like a logistic regression. Okay, and then the boundary, okay, is just like the previous example. It's going to be negative alpha divided by beta. This part, all these parts will be identical to the one we discussed previously. But now, okay, it's interesting part. Okay, pi is like a beta distribution. Alpha is 1, beta is 1. So this is obviously a flat plier, right? Okay, so pi could be, any value from 0 to 1. Okay, and then your p is going to be 0.5 pi plus, 1 minus pi times theta, and then you apply the Bernoulli to it. Okay, just like a regular binary classification, and you generate 1,000 sample. Okay, then you can see that, okay, this this boundary, okay, if you use this robust logistic linear regression, the mixture model approach, you will see that this boundary does not get affected that much by these outliers. It was still located at a reasonable location. Okay, because keep in mind, okay, for the majority part of the vesicular, they have a much longer sample length. Okay, how many entries do we have in the data set for the vesicular? 50. And we intentionally create those 6 short sample lengths. But if you try to think about it, we have 50, like a normal sample length for the vesicular, which are much longer. Okay, those 6, even though those 6 special cases, they have like a much shorter sample length. Those can be considered as outliers, right? So this robust, like logistic regression, okay, the mixture model is able to recover the correct boundary without being affected by the outlier that much. So this is a very good result. Okay, you can compare this one with like the one we have. I mean previously. I mean without those outliers, and you will see that. I mean the impact of the outlier is minimized in this result. Okay. So to talk about this chapter, I mean all the models, okay, including the one that we cover in the regression, linear regression chapter, okay, the linear regression chapter as well as the one that we cover in this chapter, all these models fall into the range, the term called the generalized linear model. Okay, because pretty much all the models, okay, here, okay, we have a linear regression, and then we apply certain maybe like a inverse link function, okay, something like that. So I mean, actually PyMC3 include a module, okay, to simplify the creation of linear model. Okay, that module is called a generalized linear model, or abbreviated as GLM. This module is actually all the models that we have talked about, okay, in the last chapter and this chapter, okay, you could use this module to create that. I mean, with very simple parameter setting, that's it. Okay, so I mean, but of course, I mean, then you may ask, why do we need to go through all those things? But because like you need to understand, you know, the original model, okay, in order to know like which model that you want to use for different application. But once you know that, okay, you could use the GLM module, just set the parameters appropriately, and that pretty much, you know, just help you to deal with, I mean, a lot of tiny details very conveniently. Okay, so for example, a simple linear regression, okay, will be just one liner. Okay, with pm.model as model and glm.glm, y is you know, tilde x, okay, and the data. That's it. Of course, I mean, because it's a simple linear regression, so it's very, very easy. Okay, we know y is pretty much a plus alpha plus beta x, right? So you don't even need to talk about alpha and the beta, okay, because those are set like automatically by the GLM. Okay, you only need to know y is proportional to x. The tilde basically means the proportion. Okay, or you can abbreviate. You can explain that tilde as y is distributed as. So it will also include that Gaussian. Remember, y, when we say y is distributed as x, it actually means y is like what should I say? It's drawn from the Gaussian distribution, where its mean is alpha plus beta x, and standard deviation is well, it's from a prior, and it will be determined by the data, something like that. So all these things will be automatically taken care of by the GLM module. Okay, so the second line of the preceding code, this one, this one, this line. Okay. Sorry. Take care of the adding priors for the intercept and for the slope. So the priors, they will be considered, they will be dealt with like automatically. Okay, if you use the GLM module. Okay, so by default, the intercept is assigned a flat prior and the slopes is going to be, you know, n, okay, with n is normal, obviously. I mean Gaussian, okay, with mean 0 and standard deviation is like a, you know, 10 to the power 1 times 10 to the power 6. So it's going to be very big standard deviation. Okay, so it's indicating it's a very flat prior. So know that the maximum a posteriori, okay, map of the D4 model will be essentially equivalent to the one obtained using the ordinary least square method. Okay, so this is like a, if you use this, I mean, this is going to be similar to least square method. I mean, but that's exactly what's going to happen if you use like a simple linear regression anyway. Okay, with a proper setting of the prior, of course. Okay, so this is totally fine as the D4 linear regression. Okay, so you can change it using prior's argument. Okay, so if you use a proper argument, you can change the prior. Okay, and the GOM module also adds Gaussian likelihood. Okay, so you will apply the Gaussian likelihood to your linear combination, and you know, by default, so you can change it using the family argument. Okay, because like the Gaussian likelihood obviously, I mean, work for the simple linear regression or multiple linear regression, but it may not work for like for example like logistic regression or even softmax regression. So, but you can change that using family argument. Okay, so you can choose from the following options, such as normal, okay, student T, binomial, Poisson, negative binomial. Okay, all these are there for you to choose. Okay, so to describe a statistical model, okay, GOM module uses PATSI. Okay, PATSI is like is a Python library that provides a formula mini language syntax inspired by the one used R and S. Okay, in the previous code block, okay, Y tilde X is the PATSI syntax. Okay, this specifies we have an output variable Y that we want to estimate as a linear function of X. So if you want to know how to, you know, how to specify the relationship between your output and the input features, okay, you need to check out this web page, okay, to know more about like a PATSI, syntax, okay. So this GOM module, as I say, is very powerful. Okay, it subsums all the models that we have discussed, we have covered in the last chapter and this one. Okay, and all these models that we covered fall into the category, okay, called generalized linear model, which is perhaps like the most important concept in the Bayesian data analysis, because the Bayesian data analysis, I mean, the majority of the models are under the umbrella of GOM. Okay, so that's about it for this chapter. Okay, so we are done with that, and we still have like about 10 minutes. So I would like to one moment. Sure. What happened? I would like to talk about this model comparison just for maybe like 10 minutes. So, who is? Here. Okay. So we know like all the models are incorrect in some sense, okay, because they are, they are designed as approximations to help us understand particular problem or a class of related problems. So models are not designed to be verbatim copies of the real world, okay. I mean, all the models will be simplified, to a degree, okay. Even when a priori, okay, we consider every model to be wrong, okay. Not every model is equally wrong, okay. So models are wrong, but some models are less wrong than the others, okay. So it's not like we are trying to get it's not like we are trying to get the correct model. It's like we are trying to get the best model. The best model in the sense that it's less wrong than the other models. Okay, so some model will be better than the others at describing a given problem. Okay, so you have to sacrifice some details. In order to create a model. Otherwise it's impossible to create a model. Okay, to accommodate all the tiny details, all the factors. In the real world, that's just impossible. So, in the previous chapters, we focus our attention on the inference problem. That is, how to learn values of parameters from the data. So we already discussed all these things. Okay. So in this chapter, we are going to focus on complementary problem. How to compare two or more models that are used to explain the same data. So all these models explain the same data, but we want to know which one is better. When I say better, it's less wrong. I'm not saying it's more it's correct. I can never say a model is correct. Okay. So as we will learn, this is not a simple problem to solve, and at the same time, it's certainly a central problem in data analysis. Okay. So this is a very important problem. Okay, a lot of time, for a given problem, you can model, you can provide different models. Which model is more plausible? Which model are not? That's an important question to answer. Okay, so in thinking probabilistically, we introduced the concept of posterior predictive check. We talked about this earlier. Okay, and in subsequent chapters, we have used it as a way to evaluate how well models explain the same data that's used to fit the model. So the purpose of posterior predictive check is not to indicate that the model is wrong. Okay, we already know that. Okay, this is the first thing you need to understand. All the models are wrong. Okay, it's just like which model is less wrong than the other, or you can say, change another better word, which model is better than the other. Okay? By performing posterior predictive checks, we hope to get better grasp of the limitations of the model, either to properly acknowledge them or to attempt to improve the model. So this posterior predictive check is one of the most important tools for model comparisons. Okay? So implicitly, okay, in the previous statement is the fact that models will not generally reproduce all aspects of the problem equally well. So this is not generally a problem given that models are built with a purpose in mind. Okay, so posterior predictive check is a way to evaluate model in the context of that purpose. Okay, so if we have more than one model, we can use posterior predictive checks to compare them. So this is the first tool you need to remember, for model comparison. Okay? So here, is a simple data set. Okay, we create this data set. Okay, something like this. Okay, and in the data, I mean, you can see that. I mean, we actually try to use what should I say, like the order of 2 to create this. Okay, so but it looks kind of flat, right? Kind of flat, very flat, to be honest. Okay, so for this data set, okay, you can obviously create a simple linear regression, okay, or you can create a quadratic regression. Okay, so the first part, okay, is simple linear regression. The second part is a polynomial regression of order 2, or how we call it, quadratic regression. Okay, I mean, the code is very simple, like to write. Okay, and not much to talk about because we have like explained this not in the previous chapter, but in the previous chapter. So this is really something that is very easy. Okay, if you still have problem with this example, then you may have trouble with this class. Okay, but anyway, just want you to understand that we intentionally create 2 models from the same data set. Okay, so the first one is called model L. The second one is called model P. Okay, obviously the first one is a linear model. The second one is a polynomial model. Okay, so that's why they get a name. Okay, and then we can plot the mean fit for both model. Okay, and it looks like this. Okay, obviously the orange one represent the linear model, and the blue line indicates the polynomial model. I mean, of order 2. Okay, so by looking, which one looks better? They look not much different, right? Okay, and if you try to use like I don't think I need to explain much here. Okay, but if you try to look at the result, okay, of the model, okay, for example, this one basically means the interquartile result of like the real data set as well as a linear model and the model of order 2, the polynomial model, and you will see that they looks. I mean the average, the interquartile. I mean they are not much different either. Okay. So what do we do? Okay, what do we do? Okay, yeah. I mean, I think we are running out of time. So today, I mean, the best we can do is I will just give you this question, and next time we will start from here. I will talk about how do we deal with that using like a posterior predictive check. Okay. So any question? Yeah, I think we are running out of time. So one thing to remind you, okay, today is actually the second last class. The next week is going to be the last lecture, okay, and the week after next is going to be the final exam, okay. So I think I gave you guys the sample final, right? Okay, and I also gave you the homework 4, right? The homework 4 is due probably next week. Is that right? Okay, just want to remind you, okay, I mean, to do that, I mean, don't forget, I mean, the homework 4 and the final exam, okay, I mean, they are coming. And also, the 3 weeks from today, okay, we have like the term project presentation, okay? So we have a lot of activities going on, okay, at the end of the semester. I just want to remind you about that, okay? So, any question? If no question, that's it for today, okay?